In this video, we are going to be discussing example problem 7.24. Definitely let me know if you need help with any particular question or any topic in your textbook. Also, let me know if you found this video helpful. That definitely helps boost my confidence and helps me spend more time on these videos. First of all, calculate the pH of 0.1 molar ammonium solution. Calculate the pH after 50 ml of the solution is treated with 25 ml of 0.1 molar HCl. The dissociation constant has been given to us. So essentially what we're doing is we're calculating the pH twice. First is for the ammonia solution itself, and the second is when we add some amount of HCl to it. So before we go forward, the first thing I wanted to talk to you about is this particular section. This is basically giving you an outline of all the steps that we will be following. Feel free to pause at this point in time, going and trying to figure out if you can try and solve this problem on your own with these points. So the first step we have over here is we need to calculate the concentration. We need to calculate the pH. That's the first thing I'm going to do because it's the easiest. So for us, for this particular solution, you have NH3 plus H2O, because we are adding water to it, is in equilibrium with NH4 plus OH minus, right? Now let's assume the concentration of NH4 plus and OH minus is X respectively, and you have equal number of the concentration of both of them are equal to each other. So essentially what I'm trying to say is concentration of NH4 plus is equal to concentration of OH minus is equal to X. Now the value of Kb, which is equal to, you have 1.77 into 10 to the power minus 5, is equal to concentration of NH4 plus into concentration of OH minus whole divided by concentration of NH3. Now this is going to be equal to 1.77 into 10 to the power minus 5, right? Now before that, we need to figure out the concentration of the NH3. Now, the NH3 concentration is going to be concentration of NH3 is equal to 0.10 minus X, because X represents the dissociation of the ammonia to form the ammonia solution to the ammonium ion. So we are going to say that this is 0.10 minus X, and this is approximately equal to 0.10 because the value of X is significantly less than the value of the concentration of the ammonia. So what we are going to do is we are going to substitute 0.10 as the concentration of X. So what we are, as a concentration of ammonia solution. So we are just going to substitute. So you have X squared, because that is ammonium ion and OH minus ion, and this divided by 0.10 concentration of the ammonia solution is 1.77 into 10 to the power minus 5, right? So now you have X squared is equal to 1.77 into 10 to the power minus 5 into 0.10, and that gives us 1.77 into 10 to the power X squared 10 to the power minus 6. Now we are just going to take root, so X is equal to root over 1.77 into 10 to the power minus 6, right? And this is going to be equal to 1.33 into 10 to the power minus 3. So this is the value of X, which is equal to the concentration of the hydroxide ion. From the concentration of the hydroxide ion, we can easily calculate the value of the pH of the particular solution. So to do that, what we are going to do is we are going to use the formula Kw is equal to concentration of OH minus into concentration of H3O plus, right? So first we are calculating the concentration of H3O plus, and the value of Kw is itself 10 to the power minus 14. So the concentration of H3O plus because we need to, for the pH, we need negative log concentration of H3O plus, right? So so you have 10 to the power minus 14 divided by, because this goes here, so you have to divide it, 1.33 into 10 to the power minus 3. Now this will be equal to 0.751 into 10 to the power minus 11, or we can just change it a little bit to 7.51 into 10 to the power minus 12. Now this is the concentration of the H3O plus. Now pH is equal to minus log concentration of H3O plus, right? And this is what we've been learning from the past couple of videos. So minus log concentration of H3O plus, which is 7.51 into 10 to the power minus 12. Now when you have multiplication, you will get, I feel like we've discussed this particular equation so many times. So you have 7.51 plus log 10 to the power minus 12. So this is equal to minus log 7.51 is 0.875 minus 12, right? Now this is equal to 11.125. So the pH of this particular solution is 11.125. I'm just going to write down. No, let me do it this way. So the pH is 11.125. That's the pH of our given solution. Now, if we had left it as is, we could have moved on with our lives, but that's not the case. They also added some amount of HCl to this particular solution. So what we are going to do is, let's calculate the number of moles of the of HCl as well as the ammonia itself. So molarity is equal to the number of moles divided by volume in liters. Now if you have it in ml, you'll just multiply it with 1000 at the top. So that will become ml, and then you can just say moles per liter, because we are still putting in the factor of conversion. So first of all, the number of moles of HCl. So number of moles of HCl in 25 ml of the 0.1 molar concentration. So I'm just going to say number of moles of HCl. And we know the conditions. So that's going to be, so essentially since we're calculating number of moles, it'll be molarity into the volume, right? So molarity over here is 0.10 into the volume. Volume of the solution is 25 ml, which 25 ml in liters is going to be 25 divided by 1000. So I'm just going to say 25 divided by 1000, right? So this is equal to 225 in, since it's in the denominator, it will become 10 to the power minus 3. So it will be 25 into 10 to the power minus 4, or we can just say 2.5 into 10 to the power minus 3 moles. Okay, so that's the number of moles of HCl. Similarly, the number of moles of NH3 will be, remember one thing, here the volume of the ammonia solution is not 25, it is 50. So 50 divided by 1000. Okay, so you're going to get 50. So you're going to have 0 and 0 cancel, and in the end you're going to be left with 5 into 10 to the power minus 3 moles. Okay, so when you, and remember, you can just double check, this is moles per liter and you have this in liters. So liter and liter gets cancelled, so you're left with the number of moles. So you can double check to make sure that you've done the right calculation. So essentially, when we have 25 ml of this particular solution getting added to this, what is happening is the number of the NH3 that is getting neutralized will be this minus the value of this. So essentially what we're doing is we're subtracting the number of, because this is lesser, right? So it uses up all of that. So the number of moles of NH4 plus that is the basically getting neutralized, is going to be 2.5 into 10 to the power minus 3 moles. I feel like the paragraph given was a little confusing, but essentially what we're doing is we're subtracting this with this, and then you're left with 2.5 into 10 to the power minus 3. So the number of moles of the NH3 molecules will be equal to the number of moles of the NH4 plus ion, which is equal to 2.5 into 10 to the power minus 3 moles. Essentially what I'm trying to say over here is that HCl is half, the volume of HCl is half of the volume of the ammonia solution itself, and the concentration of both these solutions are the same, so it is able to neutralize to the same extent. So you have half of it getting neutralized and the other half of it which stays in the undissociated form. Okay, so that's so in the 75 ml, so the final volume is going to be 75 ml. Right. Now, what we're going to do is we're going to calculate the concentration of the NH3 itself. So, the concentration of NH3 will be equal to number of moles, which is 2.5 into 10 to the power minus 3 moles, divided by 75 ml, because that's the total volume, but I'm just going to say liter because we are multiplying it with 1000. We're putting in the factor. Right. Now, this is going to give us 0.033 into 10 to the power minus 3 into 1000 moles per liter, which is molarity, and this is giving us 0.033 moles per liter. Okay, so this is the concentration of the NH3, which is going to be equal to the concentration of NH4 plus ions as well. Okay, now when we think about the new equilibrium, let me do this. Let me go a little bit lower. All right. So when we think about the concentration, when we have the equilibrium existing, what happens is you have the concentration of NH4OH is going to get dissociated into NH4 plus OH minus, right? We are assuming that the concentration of NH4 plus and OH minus is Y and Y respectively, where Y is we're assuming that this is Y and Y is the degree of dissociation. Now, when you have this after it undergoes the, dissociation, all of that, the concentration is going to be 0.033 minus Y, right? Now, after neutralization, when you have the neutralization process also taking place, after all of that takes place, what you are left with is the ammonium ions, okay, which is 0.033 molar ammonium ions, and you have this particular Y exists, right? So after dissociation, and quickly you'll realize none of this matters, I'm just going to say right now. So concentration of NH4 plus is going to be equal to 0.033 plus the value of Y. But value of Y is very, very small, so you are going to ignore it. So essentially what we are going to assume is the concentration of NH4 plus is equal to the concentration of the undissociated one, which is equal to 0.33. Okay, now in this equation, Kb will be equal to concentration of NH4 plus into concentration of OH minus divided by concentration of NH4OH. Now we assume that the undissociated and this, they're both equal because we are assuming that the value of Y is significantly less. So we are just going to say 0.033 into Y, because that's the concentration of OH minus, divided by 0.033. So this gets cancelled, so you're left with Y, and Y is equal to 1.77 into 10 to the power minus 5. Now this is equal to the concentration of OH minus, and similar to what we did previously, we can just calculate the value of the concentration of the the H3O plus hydronium ion using the hydroxide calculation, right? So concentration of H3O plus, I'm not repeating the formula because we just learned it, is equal to 10 to the power minus 14 divided by concentration of OH minus. So that is equal to 10 to the power minus 14 divided by 1.77 into 10 to the power minus 5. Now this is equal to essentially you're getting the value of this is going to be 0. When you simplify 1 divided by 1.77, you get 0.56, and when you take this to the numerator, it becomes 10 to the power 5, and then this minus this, you will get 10 to the power minus 9. Now to calculate the pH, we need negative log concentration of H3O plus. So pH will be equal to minus log concentration of concentration of H3O plus, which is 0.56 into 10 to the power minus 9, and this is equal to minus log 0.56 plus log 10 to the power minus 9, and then you have minus 0.25 plus, oh actually it was minus, I apologize, okay, minus 9, and this gives us a value of 9, and then 9.25, and this minus into minus becomes plus, so the pH is 9.25. At this point in time, you can also do it in a way where you calculate the pOH, and pOH minus 14 minus the value of the pOH will give you the value of pH. It's perfectly fine for you to do it that way. So in this question, what we did was we first started with the calculation of the value of the pH for the solution that was given to us. That was pretty straightforward. We used the value of Kb to figure out the value of pH. And then you use the formula related to molarity, and we figured out the number of moles of the ammonia which is undissociated, as well as the ammonium ion itself. In the end, we realized that the ammonia concentration and the ammonium ions concentration are the same, and then that came up to 0.033. And the value of Y is very small, so we could just ignore it when it came very small in relation to 0.033. It is not like it doesn't matter at all, but because it is significantly small than this value, we can just ignore it for now. And that gave us the value of the concentration of the hydroxide ion, and we then calculated the pH using this. And I hope all of that made sense. In the next video, we will be talking, I genuinely have no idea. I think we're talking about the next topic related to common ion effect.